So the first thing we're going to work with, the first solution to the groundwater flow equation or boundary value problem, is called flow nets. And these are what we call graphical solutions. So these are graphical solutions to the BVP. All right, and they do two things. They're going to help us develop intuition for what groundwater flow systems look like, all right, and how they behave and how they respond. But they also, under the right conditions, they allow us to make quantitative calculations of the amount of groundwater flow, the head at certain sites. So they develop intuition and they're a pretty powerful tool. All right. So they include all the ingredients that we have to have, all right, for a solution to a boundary value problem, if we have the right conditions. Let's first make some assumptions that allow us to use them quantitatively. And this set of assumptions are things that we're going to try and make a lot. All right, so assume. Steady state. Homogeneous. Isotropic. All right, and we're going to make another assumption, and that is aquifer of constant thickness. We'll address each one of these assumptions and how their effect on flow nets, but let's just make these assumptions to start off with. Okay, so let's just talk about the flow net now. So at its basis, a flow net is two sets of curves. Two sets of curves. One are flow lines or streamlines. They get called both of these things, flow lines or streamlines. And the other are they can be called head contours or potentiometric. All right, so two sets of lines, streamlines and potentiometric or head contours. And so I'll draw a really simple one, and let's think about this setting. We are, let's think about groundwater flow, I don't know, in the Hellgate Canyon, all right? So I've got this system where I've got Mount Jumbo up here. All right, and I've got Mount Sentinel down here. And remember that the river flow in general is this way. So this is the way that the Clark Fork's flowing. Now, a flow net will look like this. So I'm going to say that at some portion upstream, I'm going to say I know what the head is equal to. So this is going to be my first head contour, and this is H is equal to H1, and this is at X equals to 0. I'm going to say I know this. This is called a boundary condition. This is where I know the value of the head. I've drilled some wells. I know what the value of the head is in my aquifer. I'm looking down. This is in plan view, right? So I'm looking down. I'll just draw our little, no, I won't, because it'll get in the way. The river's going this way. Okay. Now at the bottom is my second boundary condition. H is equal to H2. And here, this is X is equal to L. So X equals to 0, X equals to L along the direction of flow. And let's say this. The groundwater flow system is generally going to be in the direction of flow. And so I know that H1 is bigger than H2. So I'm gonna start trying to draw a flow net. So we will spend some time drawing flow nets for the next few classes. Make sure that you bring an eraser, because flow nets are hard to draw. So my blue lines here are going to be streamlines. And for this particular setting, I am trying to draw these as straight as I can. And my red lines here are going to be head contours. And what I'm trying to do here with my head contours is make squares as best I can. And not all of these are perfect squares, and that's just the way it's going to be. I've had students absolutely tearing their hair out trying to make perfect squares. And it's just not always going to work that way. All right, so these are supposed to be what we call curvilinear squares for this setting. And what a curvilinear square means is that I can draw a circle in here. You'll see why we're going to draw flow nets in settings where they're these are going to be not straight lines. And so that the circle helps you define what a square actually is in the case where your streamlines are bending. All right, so these are my flow lines or streamlines. These are my head contours. These are my boundaries. Actually, I'm going to call these no flow boundaries. These are my boundary conditions. All right, so that's the terminology and the general anatomy of a flow net. I'm now going to talk about the rules of constructing a flow net that make it something that we can make quantitative calculations with. And this is for my assumptions above. All right, so rules of construction for a homogeneous, isotropic, steady state, constant thickness aquifer. Number one, flow lines. I'm going to just use streamlines. Streamlines and head contours. Intersect at right angles. So there are some rules that are unbreakable that I will definitely take points off when I look at your flow nets. I am not going to sit there and be like, oh, this doesn't look quite like a square. All right. I'm not going to quibble like that. If you made an attempt and it's close to a square, close being a key word, I'll be fine with that. But streamlines and head contours, this has to be a right angle. Has to be. That is fundamental. All right. Two, head contours. These also get called equipotential lines. It's all the same way of saying that this is a contour of a head value, right? So this one here, H is equal to H1. This one here, H is equal to H2. This is H is equal to HI. It's just a contour. of a head value. All right. That's what the equipotential line is. Or potential, head or potential, right? They're the same thing. Head contours intersect no flow boundaries at a right angle. This is another unbreakable rule. All right. These and these need to intersect at right angles. That's a fundamental thing with a flow net. So this is a no flow boundary here. The equipotential line and the no flow boundary intersect at right angles. What does that mean about a no flow boundary? If equipotentials and streamlines intersect at right angles and no flow boundaries and equipotential lines intersect at right angles, what does that tell you about a no flow boundary? It is a streamline. Hang on, minds are blowing. I just said it's a no flow boundary, but it's a streamline. This is an important distinction and one that needs to be made. When I say a no flow boundary, that means no flow across it. That doesn't mean no flow along it. It means no flow across it. So a no flow boundary means no flow across that boundary. That is why the equipotential line has to intersect it at a right angle, because that means all flow along at a no flow boundary has to be occurring along the boundary, parallel to the boundary. So a no flow is actually a streamline, parallel to the boundary. Okay. The third big one, we need to make curvilinear squares between our sets of curves. All right. So the number of head contours and the number of streamlines are not independent. There's no right or wrong number of them as long as they make curvilinear squares. All right. So I could have drawn 5 streamlines and then had more head contours, right? Some hints, it's always easier. The less streamlines and head contours you have, the better usually. But you're gonna have to vary them. All right. And this is part of the frustration and the art of making a flow net, is trying to decide how you sort of get started. For me, it's easier for me to think about a streamline because I can look at a head at one boundary and I can look at the head at the other boundary and I can tell you, oh, H1 is bigger than H2. And then I can look at these guys and I can say, well, the water is going to be going from here to here. All right. Oftentimes it's easier if you can sort of start at a no flow boundary because you know what a streamline looks like right there. It is the no flow boundary. But I usually start with a streamline. It helps me in my mind, decide what this thing's going to look like. And then I try to divide the space up as evenly as I can with streamlines, and then add head contours. As configurations change, you're going to have to do this iteratively. So an eraser is critical. All right. This is a very easy, the simplest setup. All right. If I have an aquifer where the boundaries are shrinking or that has some different geometry, life is going to get harder, and you're going to have to shrink the streamlines together and then shrink the headlines together in order to make it so that you keep curvilinear squares. So these are the 3 rules. Remember that your boundary, your constant head boundary, is an equipotential line. All right, that's your first equipotential line. This constant head boundary here is my second equipotential line. All right. Now, all other contouring rules for head remain in place. So contouring rules are, they cannot cross each other. Contours cannot intersect. That basically says I've got a head of 10 and I've got a head of 11, and where those 2 intersect, I'm saying there's a head of a 10 and a head of 11 at the same point. That doesn't make any sense. All right. So they cannot intersect. They must either travel from one boundary to the other, or they can form a closed loop. So contours, all these lines must travel from either one boundary to the other or form a closed loop. They cannot intersect. And then we have these other rules. They must intersect no flow boundaries at a right angle, and the flow lines and the contour lines must intersect at a right angle, and they need to make curvilinear squares. Okay, I'm out of time. Thursday. Let's see, next week, we don't have class Tuesday, is that correct? Next Thursday, I'm going to be in Colorado, so it's a Zoom class next Thursday. I'll be on at the right time, and I'll also record the lecture. But my pops is sick, and I got to go home. So I'll be down there in Colorado. I'll send you guys an email if there's any change to that, but plan on Thursday, 8 to 10, the Zoom link on the class. I'll be there. Cool? All right. And make sure you've got, we're going to draw flow nets in class Thursday. Come on in, Ash, just crash the party. We're going to draw a bunch of flow nets in class Thursday. I will send out that lab Wednesday. So make sure you print it off Wednesday. Okay? All right. See you then.